So welcome everybody. We will quickly go over the introduction to machine learning for the disciplines to the first session as it was shown on the 6th of April. This is an historic introduction of artificial intelligence, and what we're talking here about is, so what we find out is that basically since the beginning of mankind, humans strive for the creation of artificial humans. So the idea to build machines that act like humans is kind of one of, let's say it like this, one of the things that humanity strives for, visibly since the beginning, or something that is long time a philosophical discussion within human texts. So we go here to Hero of Alexandria, which in ancient Egypt already in 2500 before Jesus Christ built the first machines that should act like humans. Of course, these were mechanical driven machines. There was no computing device behind it and no artificial brain behind it. But it shows that already in early civilizations, the strive for human-like to rebuild humans was there. In the newer past, in the modern past, we have the Mechanical Turk, which legacy of course lives on in Amazon's Mechanical Turk, which is a program where humans also replace artificial intelligence, where basically can hire humans in order to perform, for instance, artificial intelligence labeling tasks. So the legacy of this program of Amazon goes back to this machine which was built from Kempen. In this machine, as you can see, it's a chess machine, and it should be a chess computer as we know it today. But of course at that time there was no computing device, so they put a little human in here, and it was kind of a fake machinery, a trickery that should show that one can replicate human intelligence in this kind of chess computer. But of course it was driven by human, but again the drive at least was there towards artificial intelligence, let's say it like this. We have then later in the 1940s already McCulloch and Pitts, which built a mathematical formulation of what today we call an artificial neural network. And when we look at the figures of this paper, we find the first architectures of neural networks, where we can imagine, for instance, that this is what people would today call a recurrent neural network, where we have these kind of recursion things going on. And all kind of patterns that already were theoretically discussed. And as we see, this theory already dates back to the 1940s. So AI, to say it in this respect, is a discipline that is already at least 60 years, 70 years old. So it's not something new, and the theory basically was already there, let's say, in the 1950s for many of the models that we are using today. So going back to 1954, we have Marvin Minsky, which is kind of one of the great, let's say like this, fathers of AI. He published his thesis in this year, which, as we can see, is the serial of neural analog reinforcement systems, and as he called it, the application to the brain model problem. So how to model the human brain. Again, what mankind basically strives for thousands of years already. And so we have in 1956 the Dartmouth Artificial Intelligence Conference, and at this Dartmouth Artificial Intelligence Conference, kind of key figures you find probably, if you're interested in the field, very well-known names here. And when we look at what was on the agenda of this conference, it looks like a modern machine learning conference. Of course, at that time, the computational power was not there, so mainly theoretically aspects were discussed. But later on, so we have John von Neumann, also from the 1950s, which was working on the Manhattan Project, which was a brilliant mathematician, which worked in several fields, and which also was kind of a father of computing, and whose name we kind of memorize in the von Neumann model of computers today. So he wrote a book which was called The Computer and the Brain, where he kind of theorized that computers can be used in order to build artificial brains and to create artificial intelligence. This was his last book before he died, just to note it out. So this is the story here. We then go even actual programming languages kind of were developed for this AI field. So in 1958, John McCarthy built something which is called the Lisp language. And the Lisp language was very popular in artificial intelligence for a very long time, because it was one of the earliest languages which allowed code morphing and Lisp, of course, due to the name, list manipulation. And both things were kind of seen, especially this recursive nature, the code morphing nature, seen as aspects of what a computing language should have in order to allow for artificial intelligence. So the idea was that with this kind of computers can reprogram themselves, and this should be kind of a key for artificial intelligence. Yeah? Going further, I would just introduce you to David Hübel and Thorsten Wiesel. So you have here these two key figures, and why am I introducing you to two biologists? Because these two biologists, they made this cat experiment, and in this cat experiment they showed specific patterns of light to the cat and tapped into the visual cortex of the cat and wanted to find out how the visual cortex basically of the cat worked. And they found out that the visual cortex uses convolution-like mechanisms. So in a later session we will talk about convolution and how all this works. But just to tell you that this experiment kind of was the inspiration for later convolutional neural networks that came up. So Thorsten Wiesel and David Hübel kind of got their Nobel Prize in 1981 for their experience on how basically the brain computes on visual information, and this kind of computing mechanism were then applied in later convolutional neural networks. So something else, there is also the Turing test. So the Turing test is, the idea was, what can you do in order to build a machine that you can talk to and have a conversation with without that you can recognize if it's a human or a machine. So back in 1965, a very famous computer program was written, which is called the ELIZA program. Of course, by today's standards, this is very primitive, but the idea was here to that you can have a conversation with the computer, and the computer basically asks you questions, and you can answer to these questions or ask counter questions, and the questions are made in a specific way so that whatever you kind of say, some kind of question comes up, and in this way you can have a conversation with a computer. And the idea was, well, can you distinguish if it's a computer or a human? In this case, of course, you can, but it was kind of the first step of building machines where it should be indistinguishable if you talk to a computer or to a human. We then go, as I said, to this convolutional neural networks. So after the famous cat experiment that we just talked about, I just look it up, from 1964. So we have a bit more than 20 years later, the famous LeCun, which basically is today the head of Facebook, who wrote his thesis on convolutional neural networks, and he used these convolutional networks into this new field that came up at the time, into character recognition. So he kind of could build a machine which automatically detected digits at the time. He presented this at the time, so this was kind of his thesis, to have these convolutional neural networks to recognize patterns correctly and find out, okay, is this the digit 2 or the digit 3? And he could do this for handwritten images and all kinds of different images by training these convolutional neural networks that work kind of on the same basis as this cat visual cortex that we talked about before. Yeah? We have then in the 1990s, so LeCun kind of started this already with this, but there is also the support vector machine, which is kind of a key algorithm at this time, which kind of strived in this whole kind of OCR. So what is OCR? Optical character recognition. So in these kind of days, we not only talk about digits as in LeCun's thesis or as in this as shown above here, but about all kinds of characters that could be distinguished by a machine and read by a machine. So it means you can scan a document for the first time and without having someone kind of type the text into the computer automatically can detect the text, and the text can be stored in the computer with the right letters, and the letters can be understood by further computer programs. Then we go from these early breakthroughs, let's say, of machine learning, or what we today call machine learning artificial intelligence. As you see, it took a very long time in order to get these first machines running up, and we are far from the intelligence that we expect today from artificial intelligence systems. But it really then, there was another breakthrough which came in the 2000s with programmable GPUs. So NVIDIA released CUDA, and there were kind of things, kind of precursors to this CUDA programming mechanism in order to program GPUs, so graphics cards, and these graphics cards, they brought massive parallel computing to the masses for a very cheap price, and this brought kind of the breakthrough in AI that we have today. So it's not only the algorithms, so the algorithms are kind of here since the 1950s. We then have further algorithm development, and the first, let's say, tiny success stories or applications like the support vector machine from the 1980s onwards. And from the 2000s, at least in research, we have AI as we are used today, so with perfect image description, and also then later generative AI models as ChatGPT that we are used today. So in the 2020s, for, let's say it like this, AI becomes a big topic to the general public. So before that, it was kind of in research labs. It was at least since the 2010s there, and we see then with in the 2020s, especially with ChatGPT and models, the generative models like DALL-E and Stable Diffusion, which kind of can generate images from text, for instance. That AI became a topic of the general public and of general interest. This is kind of where we stand today. So just quickly, what this whole kind of AI is. So just recap the timeline. So we have in the 1950s the theoretical concepts that are coming up. In the 1980s, we have the first algorithms that work, and we have kind of these machine learning stories that are the first courses at the universities and things like this. These are really taught about this topic and the applications that are coming up in this topic. In the 2010s, we then have what we write here as cognitive computing, so the GPUs, as I said. For the first time, we have the computational power to really build, let's say, these great tools that we have today, these great generative tools that we have today. So Then we have this machine learning topic. So as I said, it can be broken down into different parts. So we have supervised machine learning, unsupervised machine learning, and reinforcement learning, and basically all kinds of tools that we have today in AI are basically broken down to this. So most of them are kind of supervised, and there is unsupervised, is kind of this clustering theorem. So what is the supervised theory is kind of, let's go to this example of cats and dogs. So we have images of cats and dogs, and we might have, let's say, 10,000 images of cats and 10,000 images of dogs, and we show these 20,000 images to the computer. Then maybe we have one more image of this, so the 20,001st image, and then the computer automatically can detect if the 20,001st image is a cat or a dog. This is supervised learning because we show the images to the machine, we get back from the machine, we show the label to the machine, so we basically show the machine, okay, this is a cat or this is a dog, and we tell it what it is, and then in this way, basically the machine learns what to do. In unsupervised machine learning, we have a different story. So in unsupervised machine learning, basically the story is we have these 20,000 images, and kind of the machine automatically can detect, okay, well, the 10,000 of these images look different than the 10,000 other images, and you get kind of a label. So it says, okay, this is one type of image, this is another type of image, but of course it doesn't know if it's a cat or a dog, but at least you have discovered that you have two types of images. About reinforcement learning, we won't go into this course, but just we have you keep it here, as this is kind of the third pillar that is used in this kind of approach, just to keep it out here. All of this creates a paradigm change. Yeah? So the paradigm change is that in traditional computing, we wrote a computer program, we provided some input data, the program treated this data, and we got some output data. For instance, we had some boundary conditions, we ran a fluid dynamic simulation, and we got the result of the fluid dynamic simulation. In supervised machine learning, we do it different. So we have the input data, we have some expected output. So as I said, for instance, the cats and the dogs. Yeah? And we show these images, we show what is the expected output, and the computer writes the program. Yeah? So the program is written from the data, and then the program automatically can then detect, of course, whether it's a cat or a dog. So the program is kind of not created by the human anymore, but it's just like that you show the data to the computer, and the computer creates the program from the data. Okay, just to recap it here, so we have, for instance, this training data, cats and dogs, we have these labels, and then we build a model, and this model is then, of course, as I said, for instance, in this case here, in this paradigm change, built by the computer, which gives us kind of, from this training data, the label automatically for the next image, okay? Okay, we will stop here. So as I said, there are of course different types. So normally we have a chain. So the chain is kind of we perform some feature extraction. So which means okay, what is feature extraction? So if we go back, we operate on these images. There are typical features that are that cap. Is this a dog or is this a cat? Feature extraction could be, for instance, okay, well, we provide a convolutional neural network and which detects kind of edges here, and we just want to capture the edges of the image and not the whole images. This would be feature extraction. This is also kind of chained together with dimensionality reduction. So what means dimensionality reduction? So we have these images, and these images have maybe 1,000 by 1,000 pixels, which means we have 1 million pixels per image. But we want only to use kind of a few values in order to describe each image. So let's say we break this image down to, let's say, 10 values which describe this image. So we build some kind of function which brings us from 1,000,000 parameters to 10 parameters in order to tell, is this a cat or a dog? Okay. And then in the end, we train just on these 10 parameters a training algorithm, and then build our model. Yeah. So this is a typical chain, and this chain can of course be more or less depending on the task. Okay. We stop here for this introduction. Thank you so much. Bye bye.